Yeah, so we're gonna now analogize it, I guess. So going back to DNFs, a distinct DNF means that the clauses are supported on different sets of variables. And so what I mean by that is, for example, you have x1 and not x2, or x2 and x3. The first clause includes the variable x1 and x2, and the second clause has x2 and x3, which are different sets. So this would be a distinct tautology. Oh, a distinct DNF. Right. And let's do what is not distinct. So you have x1 and x2, or not x1 and x2. So clearly this would not be distinct because each of these are on the variable set x1, x2. Yeah. So any questions about that? Yeah.
Are you considering what if one was a subset of another?
What if one was a... No, okay, so...
Or are you ignoring that completely by saying they're all the same size?
Wait, can you repeat that again? So wait, before I answer that, let me give you another... Okay, so if I replace this with, say, and x3, that would be exact. Because the second one would be x1, x2, x3, and these are different sets.
Okay.
So does that answer your question?
So that is distinct.
Oh no, sorry. Yeah, that would wait. Yeah, that would be distinct.
Okay.
Right.
Yes, that answers my question.
Okay. Good. So now we're gonna look for special distinct tautology. So let me see. Okay. So first of all, here's the question. Let's define m of n. So remember, little n is like the number of variables. Let's define this to be the maximum over all s such that s is a DNF, distinct tautology. Of the size of the smallest clause in x. Okay. So we were just messing around with this and this question came up. So first let me just explain this. So what we're doing is you pick the number of variables and then we're looking at all DNF distinct tautologies, right? And we're seeing what is the maximum of the smallest clause size. Any questions about what the question is?
Maximum meaning what? You're evaluating it somehow?
Right. So this is a number, right? For each s, this is just some number. And then we're saying if you look over all of these s's, so if you look at the set of all distinct tautologies on n variables, what's the biggest you can make the minimum clause size?
The size of the clause.
Oh.
So maybe, yeah, I'll give an example. So the reason this came about is, well, first of all, you can have this lower bound of n over 2, and I'll show you why. So what I'm saying is, first of all, we knew that m of n is bigger than, well, the ceiling of n over 2. And the reason why is you can always construct something like this. So Let me just give you an example. Suppose the number of variables is equal to 5. So you split that up. Since this is odd, you say you can't divide that in 2, but you can say it's 2 plus 3. And now I'm going to make just distinct tautology like this. So you take all sets of size 2, so x1 and x2, or x1 and x3, and you keep going. So you look over all sets of size 2, and then you say or not x1, and not x2, and not x3, or dot dot dot. So is it clear what I mean by this? This is going to be all sets of size 2, and this is going to be all sets of size 3. And I'm claiming that, well, obviously this is...
The negation, actually.
What was that? Oh yeah, I forgot the negation. So obviously this is distinct. All these sets are different sets of variables. And it's a tautology because if you look at any assignment to the variables, there's going to be either 2 of the variables will be true, or if that's not the case, then at least 3 of them will be false. So one of these is going to have to be true. So it's like the pigeonhole principle. Any questions about that? Okay. So that proves, so in general you can make this construction, and that proves that m of n is bigger than or equal to the n over 2. Any questions about that? Okay. So first of all, you could ask, is this optimal? So it turns out it's not optimal. Before I do that, let me just, so this is the lower bound, now I'm going to do an upper bound. So if you know that, so let's suppose S is a distinct DNF, not necessarily a tautology, but it's distinct and the smallest clause has size equal to m. Well, then that implies that the probability that S equals true will be less than or equal to the sum I equals m to n of 2 to the minus I times n choose I. I'm going to call this number little a of n. Okay. So let me explain. I'm saying suppose we have a DNF, not necessarily tautology, so we just have a disjunctive normal form, and the smallest clause in that has size m, and it's distinct. So then you look at each clause, right? So at most your clauses could be supported on the subsets of size m, of size m plus 1, m plus 2, and so on, right? And then each of those clauses will have density 2 to the minus the size of the clause, right? Okay. Any questions about that? All right. So what is this saying? So this is saying when this is strictly less than 1, there's no way you can get a tautology, right? And so this gives you an upper bound on the number we're looking for. So if we define little a of n to be the maximum of n such that this number is greater than or equal to 1, then we have the bound that n over 2 is less than or equal to m of n is less than or equal to a of n. Because if we were to make it bigger than this number, then this probability is going to be strictly less than 1, so there's no way there can be a tautology. Any questions about that?
Particular MN is a nice sequence with RAS.
Yeah, so I'm going to get into that. So if you, well, I'm going to make a table in a little while.
Is it yet? Is it yet?
No, it's not in the OEIS. Like the first, I think, a dozen or something terms are, but if you go out far enough, it's not in the OEIS.
So you should put them.
Yeah. Okay. So we have this. And then what we did is we started just like looking for optimal examples with maple. Okay? So for example, if you just look at n equals 5, we found that m of n was equal to 3, which turned out to be our upper bound. Okay, so obviously that's strictly bigger than the lower bound, n over 2. So that lower bound is not optimal. So now the question is, oh, maybe you can always achieve the upper bound. And so we made a program to look for distinct tautologies that met this upper bound. So we use maple. We use just like a greedy algorithm to look for distinct DNFs. And the way this worked is we gave it like a bunch of sets of variables. So say we give it like subsets of variables of size bigger than 7. And then this would look for, so you need to assign, if you already have the sets, you just need to assign the knots. So we tried to assign the negations to the optimal places to make it cover the most points in the Boolean cube. Is that clear? So we just tried to make this DNF to cover the most points possible. And if we cover all the points, then we found the tautology. Okay. So, and actually this greedy algorithm gave us the optimal result almost all the time. So let me show you what we found. So here I'm going to put n. So we get all the way up to 11. And so here is A of n. So this is not hard to compute, right? It's just that thing. So we computed a bunch of these. So this sequence turns out to be 1, 1, 2, 3, 4, 4, 5, 6, 7, 7. And then we computed.
Is this an IS? This sequence?
No, this is not.
Ah.
And then we computed m of n. So obviously, if we can get an example that's optimal, then we know what m of n has to be. So it turns out we got an optimal example, except in the case when it's 10. So we know the sequence looks like 1, 1, 2, 3, 4, 4, 5, 6. But then this one, we got an example that had minimal size equal to 6. So we know this is either going to be 6 or 7. But at this point, we're not sure. And then this is 7. Okay. So questions about that? So, like we were just saying, this A of n, this is easy to compute. This is not in the OAS.
Very easy.
Yeah, so you can compute many terms of that. So soon I guess I should put that in the OAS. And if you were to plot this, it looks kind of linear. So something like that. And the slope of this turns out to be approximately, where is it? Approximately 0.678. No, 0.768. So obviously bigger than a half because we know we can do better than a half. So questions about that?
So except for 10, the AN equals MN so far?
Right, so we know for sure that except for 10, these two numbers are equal. And then at 10, they could be equal. It's just we haven't found an example to show that. So yeah, so now let me write down now. This is our conjecture. So we have a conjecture that M of n, that's the biggest size of the smallest clause in your distinct tautology. We conjecture that that equals A of n, which A of n was the most it could possibly be using that bound for all n. So that's our conjecture. And like I said, it really looks like it should be true, except we didn't. I mean, this, who knows? So if you could disprove that, that would disprove the conjecture. Any questions about that?
I think it's more prudent to call it a question.
Question. Okay, so that's our question.
Because the evidence is not.
Right. And so I have a couple more minutes left. Let me just go really quick now. So what I said in the abstract was not wrong. I did want to do like an actual generalization where, so it's basically now the variables can be 0 or 1, but we did a generalization. What if they could be, 0, 1, or 2, or something like that? So you, instead of the Boolean cube, you have a box, and each side has width that could be bigger than 2. But instead of doing that, let me do another, not generalization, but just another analogous thing to integer covering. So we can also do exact. So we can define an exact enough. And all that means is the clauses cover disjoint sets in the Boolean cube. So the clauses cover disjoint subsets of 0, 1 to the n. So for example, if you have x1 and x2, or not x1 and x3, this would be exact, because there's no point that belongs to both of these, because this one says x2 has to be true, this one says x1 has to be true, this one says x1 has to be false. So it covers disjoint sets in the cube because of this. Any questions about that? And so the other question we asked is, well, first of all, and this is the same as for integer covering, there's a theorem that says you cannot get an exact, distinct tautology. Okay. It cannot be both on different sets of variables and yet they cover disjoint subsets of the cube. So you can't do both of those. Okay, but what we were looking at, the question is, can you get something that's almost that? So the question was to find an exact and almost distinct tautologies. Okay, and I just wanted to do one more. I'll draw a picture in the n equals 3 case, and then I'll stop. Okay, so let me show you what I mean. So in the n equals 3 case, you can find one by hand, and then our question was, can you just automate this with Maple? So if n equals 3, your set of all assignments is just like, it's a cube. Right? And so now to be exact, that means we want to pick a bunch of edges or faces that are disjoint and distinct. When you think about it, all that means is you have no parallels. So you can't have, for example, this edge and this edge. That would make it not distinct when you think about that. So let's just see if we can find a almost exact distinct tautology. So one thing you could do is start with this edge over here. Okay, and then so that would eliminate like this because you can't do parallels, and also you cannot choose anything that intersects that. So there's a few choices, but one example is you can do this. So that's neither parallel to that nor intersecting. Okay, and then you can pick another one. This one here. Okay. And then the problem is at this point, you're kind of stuck and you're left with these 2 points that you can't cover without rooting the distinctness. So let's just throw those in. Okay, and when you do that, this is the DNF that you come up with. So the red, if we use like this direction is x1 and blah, 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 the red one is, so x1 has to be 1, right, and x3 has to be 0, and x2 is arbitrary. So the red would be x1 and not x3, and then the blue would be not x1 and x2. What?
It's clear.
Right.
Answer questions in fragments. Okay, so it does, sorry, I have to interrupt, because it's big one, but it's clear, beautiful picture. So you can